This video from the Foundation series of GMATMathPro.com explores special right triangles. Specifically, we'll look at 30, 60, 90 right triangles, 45, 45, 90 right triangles. We'll look at some examples of each of those, and at the end I'll show you how the ratios for those triangles are derived. So first we'll look at the 30, 60, 90 right triangles, which are named after their angles. You can see it's got one 30-degree angle, one 60-degree angle, and one 90-degree angle. And their sides are always related to each other in the same fixed way. You can see here, if you take the side across from the 30-degree angle, the hypotenuse is always 2 times that, and the other side is always root 3 times that. So here are examples of 30, 60, 90 right triangles, and a basic problem might be to find the remaining sides. So let's take a look at how we would do that. Okay, so here we have the two examples on the left, and on the right we have a general 30, 60, 90 right triangle expressing the basic ratios of the sides. So if you look at the problem on the left and compare it to that triangle on the very right, you can line the two triangles up and see that x in this case is 4 because it's the side across from the 30-degree angle. So that means that the hypotenuse must be 8 because the hypotenuse is just 2 times x, and this side across from the 60-degree angle must be 4 root 3. So if you start with the side across from the 30-degree angle, it's a very straightforward problem. If you don't, it's a little harder, but still pretty simple if you look at the relationships between these two sides, from the 30 and the 60. Now, if you go from this side, if you're given this side and you want to go to this side, it should be clear that all you're doing is multiplying by the square root of 3. But if you're given this side and you want to go to this side, then you're just going to do the opposite, which means you're going to divide by the square root of 3. So again, if you want to go from the small side to the bigger side, multiply by root 3. If you want to go from the bigger side to the smaller side, divide by the square root of 3. So that means that this side would just be 5 divided by the square root of 3. And usually we would want to rationalize the denominator in this case. Now, if you're not familiar with this tactic, you might want to go back and watch the video that we did on radicals. But here, all we're going to do is multiply the top and the bottom by the square root of 3, and that's going to make the top 5 times the square root of 3. On the bottom, we get 3. So it's just a way of getting rid of the radical in the denominator. So this side, the preferred way to write it would be 5 times the square root of 3 over 3. And now that we have that side, we know the hypotenuse is just going to be 2 times that, so this would just be 10 times the square root of 3 over 3. Then there's 45, 45, 90 right triangles. Again, it's named after its angles, 45, 45, and 90. These are also sometimes called isosceles right triangles because, as you can see, the sides across from 45 degrees are always equal. And the hypotenuse is always the square root of 2 times one of those other legs. Here are some examples of 45, 45, 90 right triangles where we're asked to find the missing sides. So let's take a look at how we can do that. Okay, so we're going to do these examples a lot like the way we did the 30, 60, 90 right triangle examples. On the first one, if you just compare the example on the left with the basic ratio triangle on the right, we can see that x is just equal to 3, which means this other side must also be equal to 3, and then the hypotenuse would just become 3 root 2. So you're just plugging that x value in to every x on the triangle. Now, just like in the 30, 60, 90 right triangle, in this one, if we're going from a leg to the hypotenuse, we're going to multiply by the square root of 2. If we're going the other way, we're going to do the reverse operation, which is division. So we will divide by the square root of 2. So to go from the hypotenuse in this example to one of the legs, we would divide by the square root of 2. And again, we will rationalize the denominator by multiplying the top and bottom by the square root of 2, which gives us 6 root 2 over 2, and then 6 over 2 reduces to 3, so that gives us 3 times the square root of 2. So both of these sides would just be equal to 3 times the square root of 2. Alright, so let's take a look at how these special right triangle ratios are derived in the first place. First, we'll start with the 45, 45, 90 right triangle. So if we draw one of those, because its two base angles are equal here, we know it's going to be an isosceles triangle, so that's how we can justify labeling these sides both x. And we don't know what this side is going to be yet, so we'll call that C. Now, since this is a right triangle, we can use the Pythagorean theorem to write an equation like this: x squared plus x squared equals c squared. And x squared plus x squared is 2x squared. And then to get a value for c, we would take the square root of both sides. And that would give us c is equal to the square root of 2x squared. Now, there is a property of radicals that says if you have the square root of a product, that's equal to the product of the individual square roots. So that means c is equal to the square root of 2 times the square root of x squared. And the square root of x squared is x, so that gives us the familiar x squared root of 2 that goes here on the hypotenuse. Now, for a 30, 60, 90 right triangle, we need to start with an equilateral triangle. In an equilateral triangle, all the sides are the same, and so all of the angles are also the same. And if all the angles are the same, they all must be 60 degrees. So that's 60, and this angle on top is also 60. So to produce a 30, 60, 90 right triangle, we can drop an altitude from this top point to the other side and make a right angle with the base. And because of the symmetry of an equilateral triangle, that altitude is going to break it exactly in half. So these angles are both going to be 30 up here, and these sides down here are going to be congruent to each other. Now, if we label this x, since these two sides are congruent, this must also be x. So this the total length of this side down here is 2x. But it's an equilateral triangle, and all the sides are the same, so that must mean these sides are also 2x. Now, if we label this altitude that we dropped b, we can again set up an equation based on the Pythagorean theorem: x squared plus b squared equals the hypotenuse squared. So that gives us x squared plus b squared equals 4x squared. We'll subtract the x squared on the left to the right, which gives us b squared equals 3x squared. And again, we'll take the square root of both sides, and that'll give us b is equal to x times the square root of 3. So we can replace that b with x square root of 3 to get that familiar form.